What's up YouTube? My name is Drew and I wanted to share with you the reasons that I personally bought a used Tesla Model S instead of going with a Tesla Model 3. Now, I'm sitting in a 2016 75D, which means this is the all-wheel drive model. And in my opinion, this far outweighs even the ability to buy a 2020 Model 3 at the same price tag. Now, I will caveat one item. Originally, when I purchased this Tesla, the stance from Tesla was that the 2015 models or newer of the Tesla Model S would be capable of full self-driving. That is no longer the case. I guess they backpedaled on that, and the 2017s or newer are capable of full self-driving. The only thing that I am missing is the two cameras on the side. So I will preface this by saying I would suggest a 2017 Tesla Model S. And if you go on Car Gurus right now, we're in the month of July of 2023, you'll notice the price tag hovers around $30,000 to $35,000 for a used Tesla Model S with around 50,000 miles on it. Hey y'all, I did want to cut in and clarify something. I mentioned that this did not have the full self-driving capability, but it does have the full autopilot functionality, and that is actually what I think many people initially kind of think of when they think of a Tesla, is the autopilot function. Now, I've always bought used cars my entire life. I typically shoot for something with around 50,000 miles, and I'll carry that all the way through around 150, and then I'll typically upgrade whatever my vehicle is. I've had trucks, I've had cars, and now I have an electric Tesla Model S. So just quickly, want to go through a couple of things that you should consider. I will make this brief. First and foremost, the 2016 and 2017s do have free supercharging. Now, it's not guaranteed with all of the Tesla Model S, so it is something you'd want to look at with the dealers, but that was a huge selling point for me because I do like to take road trips, and in this vehicle I have traveled, actually I purchased it in Atlanta, which is about 6 hours from where I'm located. Didn't cost me a thing to drive there, and mainly to drive back because I bought it there. But it didn't cost me a thing to drive all that distance. And so I've done many trips since then, and it is so cool to be able to just swing off, supercharge real quick, hop back on the road for a total price tag of $0. So that's something you want to check out for if you're in the same boat as me. Part two is the styling. I will show some B-roll footage of my Tesla, and this is, as I mentioned, a 2016. It would shock me if you had the ability to recognize that this was anything older than a 2020. This thing is in pristine condition, and they haven't updated the Tesla Model S body style until I think it was 2021, maybe 2020. It became slightly wider. The wheels became slightly wider, and again, it's a subtle tweak where honestly I only think Tesla owners can notice it. Everyone else that has approached me about my car thinks that it's brand new, which is fantastic. The next thing is actually in terms of the size. So it's no secret the Tesla Model 3 looks smaller, but as someone who has had the ability to drive a Model 3 for a week time frame, not only traveling 3 hours away, but also doing my daily commute, I personally found that while the seat is comfortable, I would actually say the seat is more comfortable than a Tesla Model S. Caveat, depending on who you are, I have some back problems, and so I actually like the sturdier, more bolstered seats of the Tesla Model S versus the Model 3. The Model 3 very much so feels like a recliner. It's extremely soft, and so at the end of my 3-hour trip, my back and my butt was actually starting to hurt. So sizing though, there's much more leg room in terms of the interior space here. And next up is actually in the functionality. So let's caveat it by saying 2017 and newer Tesla Model S quite literally has all the same technology, or I should say capability, as the Model 3s and the Model Ys, all of that new stuff. So you can in fact have full self-driving in your Tesla Model S. It's much sportier. You'll have access potentially to the free supercharging. And the other item too was the difference between braking, believe it or not, in the Model 3 and this Model S was substantial. On my road trip in the Model 3, I had issues where whenever I would need to stop abruptly, I felt like the Model 3 didn't really have it in it, which was kind of an issue. I've not experienced that in the Model S, and again, this is not a performance model. Now, last thing I do want to touch on is actually the battery. So in terms of battery, this is a 75D. You could also, in that 2016, 2017 era, you could get a 90D or even 100D. So certainly I would suggest going for as big of a battery as you can. But even on my 75D, realistic actual road trip mileage is about 230, 235 miles. It supposedly says it'll go 275. I don't buy it. It's really more so 230. So from a battery standpoint, the Model 3 does reign supreme. However, in terms of supercharging speeds, this car will charge relatively quickly. The Model 3 is a bit quicker, but I find that on the same exact road trip in the Model 3 versus my Model S, I had to sit at the supercharger for about 10 minutes longer in the Model S versus in the Model 3. So in total, it's about 20 minutes of a stop with the Model S to get back on the road, and then in the Model 3, I found it to be about 10 minutes. So that is quick. My typical gas station stops whenever I go in, use the bathroom, get snacks, is about 10 minutes. So it did cause me to sit in the cabin for an additional 10. So that's something to be aware of. But in my opinion, the styling, all of those things that I mentioned are far and away a better buy in terms of getting the Model S versus the Model 3. So those are my thoughts. It would really help me out quite a bit if you could like and subscribe the video. I know people say that all the time, but if you're trying to grow a YouTube channel, it's really important. So please consider doing that. I'm gonna post many, many more videos, not only on my Tesla, but I'm gonna review and share my thoughts on some of the other fun purchases that I've made. I think that I do have kind of a layman's opinion. So with that, I'll let you guys get back to it. Thanks.
The scientific version of mining Bitcoin when you're
effectively,
sleeping.
yeah.
You're gonna go to BitTorrent.
It's pretty much the same thing as mining Bitcoin, actually.
I see.
Anyway, same idea.
Just real quick before you go any further, for my own sake, approximately what year are we at right now? Because like a lot has happened. This started around like the 50s and
Yeah. So the ARPANET was proposed in 1966.
Okay.
So there was a decent amount of time between ARPA being spun up and this network being proposed.
Yeah, for sure.
Right. That's kind of a theme throughout this episode is there are large chunks of time between these new technologies being invented and actually getting rolled out. Like you're going to see the timeline gets kind of wild. But this is actually pretty good timing because this guy that was working on the development of the ARPANET at a US government think tank, as well as a separate guy in London, came up with an idea called packet switching. Do you guys know what packet switching is?
I've heard the term, but if you asked me to explain it, I would not be able to.
Okay, I was gonna say it sounds like one of those things where someone's like, "You're a nerd. What's packet switching?" I was like, you wouldn't understand." But I actually have no idea what it is. Yeah.
Well, so before packet switching, everything was circuit switched, which means that you had to have a direct line connection from like one node to another. So think about an operator that would connect your phones together. What he was actually doing was literally switching the circuits.
May I help you?
Yeah, operator, where's the nearest telephone?
You're speaking from the nearest telephone.
Oh,
You were literally connected directly to the other
Wild
phone,
to think about.
which is insane,
Yeah.
right? Yeah, that's really insane. But a packet switch network is pretty different. So basically, the data that we have on our computers that we're sending to each other can be broken into packets. And a packet usually is like, 8 bits or something, a byte of data, some sort of data. And it gets broken into these packets and sent through various routes in the network, depending on which like line has the least load. So usually on a circuit switch network, you have to go directly to each other. But now you kind of learn about this in like queuing theory and computer science 101. If you have all of these different lines, there's going to be different amounts of load on each line, right? So if you break your data up into a bunch of packets, each of those packets can go on a different line that has the least amount of traffic. So you can see it like 8 lanes on a freeway, right?
I was just gonna say, I wish I could do this driving to work in the morning.
Yeah. If there were, and-
Waze is just packet switching for cars.
Right. Funny enough, there's actually a thing in traffic theory where like this is like it's crazy. Traffic theory is very similar to like liquid flow theory,
Fluid dynamics,
where adding more lanes doesn't actually make traffic go faster. So it's not the perfect analogy, but imagine you're at the grocery store, right? And you want to make hamburgers for dinner and you have 5 family members and there's 5 ingredients and there's 5 checkout lines. It would be faster for each person to take one thing, check out at the same time, go home and build the hamburger. Right. Instead of like waiting in one line and then checking things out individually. You're basically doing it 5 times faster. So that's basically the idea of packet switching is you're breaking data up into little packets and then you're sending it over this distributed network. So in a network, this actually helps create something that is decentralized or more accurately distributed, because there's 3 types of networks. There's centralized, decentralized, and distributed networks. Okay. And this is actually a distributed network. So imagine that DARPA connects 4 different universities, right? They're each connected to each other. They're not just connected in a line. And they can send data in packets. And that allows them to send a ton of data through the queue with the least stuff in it. So the data knows what order to rearrange itself in, because it's got a little tag on it that says, this is the first part of the data, and this is the second part of the data. Because data is just like bits, right?
Streams of
ones and zeros, but it knows like this is the first chunk, this is the second chunk, this is the third chunk, and it can rearrange itself. That allows for a lot of data to pass through in a much faster distributed way because data is traveling at the speed of light, right? So even if you drop packets, that's not a problem because you just resend it. If you're traveling at that speed, it's like, oh no, I dropped. You've probably seen this before, like dropped packet loss, dropped these packets. There's like interference or something in the network, but it's like it doesn't matter because you're just sending data through.
The best thing to use when you like miss a kill in Valorant, just be like, oh, packet loss. Damn it.
Wow. My ping. My ping. Yeah. Anyway, so they get the first nodes set up in 1969 for this new ARPANET, right? And this was running on the 1822 network protocol, which was implemented in 1970. So it's just like time is going by slowly. Like they get the node set up, the next year they get the protocol implemented, and the protocol is basically saying like, how is this data going to transfer across the network? How are the computers going to handle the data flowing between them? So the network gets turned on in 1971, and it actually works really well. And there's this really funny story about when they were at the ARPANET and they were first starting to use it. And they connect all the computers together and they're getting all excited. And they want to log into another computer remotely because that's what you're doing if you're doing packet switching, right? You're like, let's do remote desktop. So they type L, and the other person on the other side of the line says, yep, got the L. They type O, and then the other person's like, yep, we got the O. They're trying to type login. They type G, and the network crashes. But, it works. And they had to do some modulation to fix it and make it a little better and like actually make things work. But that was the foundation of the ARPANET. So they got the first computers connected and it gets rocking.
Andrew just brought up a really good point that the very first electronic message ever sent might have just been L.
It was the original taking an L on the internet.
Yeah.
Imagine you took the first L on the internet.
The first L on the internet.
And you didn't even know it.
Yeah.
So over the next few years, the packet switch network idea starts to really take off. All of a sudden, you get a ton of universities and organizations that are using their own packet switch networks with things like Ethernet that had just gotten invented. And there was something called Token Ring from IBM, which had a really small community. And Xerox invented a new protocol called PUP, and there was a French Cyclades network, right? Like this was the way of doing packet switching was just how you send data over a network. Okay. So all of a sudden, we saw all these networks getting set up.
And these are all individual networks only connected within themselves.
Correct.
Not quite what we have today.
Correct. Okay. So it was just, the French had their own network. And then everyone was creating their own little like protocols, right? Because the ARPANET was running on the 1822 protocol. But Token Ring was running on something else just at IBM. Some universities make their own protocols that only ran at those universities.
So it sounds like at this point we have a bunch of little internets.
Bunch of little networks.
Yeah, I have to keep reminding myself that they're just logging into these other they're remoting into these other computers. This isn't like creating this crazy internet that we have today.
Right.
Like, this is super basic.
They're using each other's processing power.
Networks.
They're sharing data. They're sharing files. But it's within a small network.
A bunch of local networks.
Correct.
Yeah.
A bunch of intranets.
Intranets.
If you will.
Yeah. Networks, yeah.
Also, there isn't standard networking infrastructure yet, which is why a lot of these networks have to run on separate protocols. Like
because the 1822 protocol was like DARPA, right? Like they weren't going to just tell people how to run these networks.
Yeah. Well, and also, in the United States, we had this like full network of phone lines set up. So when these first universities were setting up, wanted to connect via the ARPANET, they literally just reached out to the phone companies and said, hey, can we lease some time on these lines?
So the University of Hawaii actually had this thing called the Aloha Net, which was basically doing packet switching over radio, which was really awesome.
That is really cool because before we were doing straight phone lines. Yeah. So radio, this is like kind of like the first wireless.
Yeah,
almost, if you want to think about it.
They showed that you could do packet switching over any type of network, which
That's
is really cool.
Yeah.
We're going to take a quick ad break, but there's a lot more to the story. It gets very exciting, so make sure you stick around, and we'll catch you on the other side. All right, we're back. Welcome back to the Packet Switched podcast. Like we talked about before, there was all these networks that were being set up, right? But when you set up a network, you're buying this box from whatever the vendor you were using gave you, right? So you ended up with a software stack of applications that you could use on top of it, and that was basically it.
Okay.
It was like they gave you this black box to set up your network, and they ran all the protocols, they ran all this stuff, and you couldn't really do a lot to it. So now all of these vendors have their own protocols, their own data rates that they're transferring data over. None of these companies cared if their networks interconnected, and they probably actually liked that, you know? It was like using Android and iOS. Like Apple likes that iMessage doesn't work with Android because it keeps you in their ecosystem, and all these companies wanted to keep you in their little network ecosystem. It's the same thing.
And there's some level of control maybe over reliability or materials used, things like that.
All these things.
Cool.
Yeah. It's just a thing we have in tech.
Yeah.
Well, and also, it was all like separate. Like in order for everything to work together, there would have had to been a conscious effort from all these different groups to be like, let's build one thing.
Right,
you
which
know?
they don't want to do. I mean, you can see this playing out today with iMessage, WhatsApp, Telegram. They all basically do the same thing, but none of them actually talk to each other, right? There hasn't really been a universal messaging protocol that for internet messaging that
RCS.
yeah, well,
Bless you.
the best thing we have is RCS, but you know how that's played out so far. Hopefully that comes into play eventually, but yeah, RCS. But pretty damn quickly, the Department of Defense started taking notice of all these networks, right? And as more of these distributed package switch networks got set up, the government was like, wait, we should use this in war. Right?
Pretty
Evergreen.
classic.
Yeah.
Classic government move.
Yeah, they could take a distributed communications network and they could hook it up to, you know, like planes and tanks and automobiles and all of these different things, because at this point, computers are getting more popularized, and computers that were running on tanks or planes were going to have a strategic advantage over a plane or a tank that didn't have a computer in it. That was just the way it went.
Yep.
Some people think older people don't know how to use the internet. I have news for you. We invented it.
It's possible to invent something and be totally behind on how it works.
For real.
I'm just saying.
Well, you wouldn't say that to Vint Cerf. He's actually he was working on the early ARPANET design as well, and he helped get a lot of this stuff online. Also, he's one of the most important people to ever contribute to the internet. He is in the Internet Hall of Fame. He is considered like Internet Zaddy.
Hall of
Oh yeah.
There's an
Internet Hall of Fame, yeah.
the Internet,
Hall of Fame, which is like the most important people to ever contribute to internet networking.
How much Reddit karma does he have?
Probably unbelievable
Probably a
amounts.
lot.
Yeah, if you talk to any like
Whoa.
data systems engineer or any like computer science graduate, he's like their like
Wayne Gretzky.
Yes.
I don't know that reference, but probably
Yes.
A lot of goals.
Probably yes.
A lot of goals.
He's a very important person.
Long career.
Yeah.
The blank stare was everything I've ever wanted in life.
His title.
LeBron James.
His title at Google is Internet
No,
Evangelist.
it's Chief Internet.
Chief Internet
Oh,
Evangelist.
wow.
And he works at Google, and his title is literally Chief Internet Evangelist.
Man, as if the internet needs evangelizing.
Well, you think it doesn't, but surprisingly, we'll get to that later.
Okay.
And in the spring of '73, a guy named Bob Kahn, who had worked very much on the ARPANET design, left Bolt, Beranek, and Newman and went to DARPA. And he showed up in my office at Stanford in the spring of '73, and he says, "We have a problem." And, you know, I'm thinking, what do you mean we? And he says, the Defense Department has reached the conclusion that computers could be useful in command and control. But the implication of using computers in command and control is that you'd be putting computers in mobile vehicles, ships at sea, and in airplanes, in addition to dedicated computing facilities. Well, the ARPANET was built out of computers that were in dedicated computer rooms with air conditioning. Everything's all interconnected by dedicated telephone lines. And you can't connect an airplane to a telephone line. That doesn't work. The cars don't work, or the tanks, they run over the wires. That doesn't work. Ships get all tangled up.
Funny guy. Funny guy. But it's true, right? So the government noticed how well packet switch networks were working. So they started spinning up satellite-based packet switch networks because that doesn't use a line, right? You could actually connect that to pretty much any type of military vehicle. And they called that SatNet, right? So they made a radio-based packet switch network because the military realized it's crazy useful to command and control. And suddenly they want computers in airplanes, and they want them in tanks and boats. And they spun up like all of these different packet switch networks with different data rates and different packet sizes and different latencies because they're all package switched, right? So you need different data rates and latencies and stuff with tanks and airplanes and stuff because they're far away.
Yeah.
You have the inverse square law for like data transfer.
And they all do different things and probably all have different requirements for bandwidth and what types of things you're actually sending over that network.
Right. Yeah. And the thing is, like, the government and the military have different, there's the Air Force, and then there's the
Navy.
the Army,
yeah.
right? So they're all spinning up their own different packet switch networks, but they're not really communicating that much, and that becomes a problem. So in 1973, they go to Vint and they say, we've got a problem. We need something that can allow all of these networks to talk to each other because we need all of our military applications to be able to communicate.
We're looking at 4 different packet switch technologies, all of which are different. They're different data rates, different packet sizes, different addressing, different latency. It's just all different, but they're all packet switched. So the question is, how do you take all those different kinds of packet networks and connect them together in a way that makes everything look uniform? That was the internet problem. And we spent from the spring of 73 to the fall of 73 trying to figure out how to do that.
Okay, can I just take a second and the internet problem, right? You have all these networks.
Mm-hmm.
They're all packet switch networks.
Nets.
Networks, network. Inter-networking problem, right?
This is the connection of all the other networks. We're finally bringing everything together.
Yeah. Because inter means everything under one umbrella. And we just take the word internet for granted right now, but it's like, it means all the networks are now connected. You're making a giant network of smaller networks.
And this was just the government's networks. This wasn't every network from all the schools and from everything else, but it was combining several networks that were being used for several different things into one huge network. Internetwork. Okay.
Internetwork.
I don't know why this reminds me of it, but this is like when Xbox first came out and you played like split screen, and then you started going to your friends and you played like interconnected like LAN parties, and then Xbox Live comes out, and now it's like I don't have to go to my friend's house with 8 other friends to play 8-player. All of us can sit.
No,
at
that's
our house
exactly
and just
correct.
play. Yeah,
you have your own little network when you're doing like a LAN party,
Yeah.
and then all of a sudden you're on the internet. Yeah, a bunch of little networks.
And it's funny to think that at the time there were computer scientists working on networking, and then there were computer scientists working on
Internetworking. Yeah, really awesome. So how do you get all these computers to talk to eeach other? That's a big problem because they're all using different protocols, different data rates, different all latency, all of these things. So, like Vint just said, between 6 months, they came up with a way to solve the internetworking problem.
We eventually came up with a protocol we call the Transmission Control Protocol, or TCP.
Have you guys heard of TCP before?
Oh, we're starting to get into modern terms. Yeah, TCP, IP, all these things are starting to sound familiar.
TCP IP.
Okay.
Insane clown posse.
Yeah.
So TCP, yeah.
So Transmission Control Protocol and Internet Protocol. And these are the protocols that allow all these different networks to talk to each other on the internet. Right? Very cool. Vint Cerf invented TCP IP. Probably the most
I can see how he's in the
important thing
Internet
ever.
Hall of Fame. That makes sense.
Yeah.
That guy's pretty good.
In like 6 months.
Okay, that's pretty good.
Yeah,
That's pretty good.
He's very important. But yeah, TCP is basically a list of agreed upon actions that allow these networks to communicate and pass data between each other and let that data stay intact so that, if you drop data, you can just throw it back in. Back then, it meant that if your computers and your network can use TCP, you can connect to any other network that's also using TCP. The local network at the University of Southern California could now connect to the local network at the University of London. They could share their research. Yeah. It was
like the USB of internet protocols.
basically like a standard. It was a standard.
A standard.
Right. So scientists can now communicate with very early forms of email across the entire world. Because they had email when they first set up these networks. It was very primitive, but it was like there was an email protocol, which is why this is the reason that you can use Gmail or Spark or whatever. You don't have to, like, if you think about like Telegram versus WhatsApp versus like iMessage, those all use different protocols, but there is an email protocol. So that Gmail and Spark and Outlook and
IMAP.
Yeah, it doesn't matter what client you're using, you're sending the same data and it's getting across, which is dope. Like, I wish you could send a Telegram message and it came through on WhatsApp, but you can't. Anyway.
Evergreen.
So they were working on TCP for a long time. They had 4 different iterations of it. They made a lot of mistakes, and it took them 10 years, right? Like, they came up with the first iteration of it in like 6 months, but it took them 10 years. Within that span of time, the first cell phone came out. The first digital camera came out. The VCR came out. The first Apple computers came out. The GPS, the Walkman. Basically, like, an insane amount of technology came out in the 1970s.
The first season of Retro Tech right there.
Yeah, exactly. Pretty much.
Solid.
Pretty much. All from the 1970s.
Yeah.
And Vince says they pretty much finished the protocol in 1978, but it took them 5 more years for it to get implemented.
Huh.
Yeah. So there are large spans of time between any of this stuff happening.
So we shouldn't expect Mastodon to have any sort of reckoning in the next year. It's probably going to take a while for a new standard to hook up.
If we ever have a universal standard for that, it's probably going to take 10 to 15 years.
It's going to take a long time.
Yeah, and it's probably because it's not being implemented by the government. This was the government.
Yeah.
Right?
That feels like the big difference between back then and today is like this all started through the government.
Right. This is kind of a tangent, but like the only reason that the internet or that email was able to do that was because it was kind of run by the government. We just didn't have internet messaging that the government created, right? Internet messaging was created in an era where private or public companies, private companies created all these messaging clients. So it wasn't the government that said, you guys all have to use this, right? Anyway, to get TCP/IP implemented, you still had to force everybody to use it. That was a problem, right? For a universal protocol to work, everyone has to be on board, which is why I was so excited for this Matter episode, because everyone started using it, and Matter is basically TCP/IP, which is awesome. It's like it already exists. I mean, Matter used to be called CHIP, which is Connected Home over IP. It literally is IP. It's Internet Protocol, which invented. Crazy, right? And since everyone's signing on to use the protocol, everyone becomes happier. But Vince, like, we need people to use TCP/IP. So he makes this absolutely baller move. He knows that everyone's going to be happier if they're using it. And there are benefits to the military for that happening too, because DARPA is a military organization at the end of the day, and they need command and control to be able to communicate. And researchers are going to love it. And Vince just like, no, I have to force people to use TCP/IP, even if they don't know it yet. Right? That they're going to love it. So Vent goes to everyone on the ARPANET, which again, there's all these research universities and stuff, and it's being funded by the government, but there's still research universities doing their own thing, and they create their own little networks, and they don't really want to use TCP/IP because they're using their own little networks. They don't really care. So he goes everyone to the ARPANET, which at that point is about 400 computers, and he tells them, you all need to switch to TCP/IP by January 1st, 1983, or you're off the network.
Power move.
He's basically like, we are cutting off your funding. We are taking your computers. You have to use TCP/IP.
And he has that type of control?
Yeah, because it's being funded by ARPA, which is the government.
Oh,
they were funding these research projects, and they're like, we literally will come in and take your computers.
Just turn off your access.
Yeah. And they didn't want that. By this time, this is like 15 years into this project. They're like hooked into using computers. Imagine if somebody came and were like, we're going to take your computers away if you don't just switch this protocol, you know?
Guess we're switching.
So by the time 1978 rolls around, we are basically ready to freeze the protocol spec after having gone through 4 iterations and start implementing like crazy. We get to the point in 1982, or late 81, early 82, where we are now ready to force every computer on every one of the networks supported by ARPA to switch over from the earlier ARPANET protocols to the internet protocols. And so we set a deadline of January 1, 1983. There are only 400 computers involved, and said, you all have to be running TCP/IP by January 1, 1983, or you're off the net. And so everybody sort of there was some grumbling about that. But since I was running the program at the time, I could say things like, you know what, if you're not on the net by January 1 of 83, I'm not funding your research anymore.
And what was
Lots
that?
Of incentive.
What was
Lots
that
of incentive.
program that you were running technically? Was there a name for that?
Well, it was the interneting program.
The interneting program.
Wow.
Yeah. Like we take that for granted now, but
Yeah.
serious.
Someone had to flip that switch to get us all together.
Yeah.
Get them all together.
Yeah. Yeah.
So he gets that switch flipped. Now all the 400 computers that were all using whatever older protocols are all now using TCP IP.
Mm-hmm.
They can all now talk to each other, and all future computers that use TCP IP can all talk to each other. It's a pretty good starting point.
So in between, or right around now, TCP and IP actually got split.
Right.
Which is why we just call them IP addresses instead of TCP IP addresses. And the reason for that is pretty nifty. The important part of the IP part is the addressing part, which if you listen to part one of this whole thing, you'll know is like this big complicated thing that needed to get figured out. So they said that IP addresses should be universal for all devices that are now connecting to this internetworking project. But TCP isn't the best way to get data across in every scenario. For example, TCP sends confirmation back, like, hey, I received each packet, which is useful if I'm trying to send you like a Word document and I need to know that you missed a few words. But for example, like the lights behind you in the studio, they work on an internet protocol. But if one of the packets gets lost when I'm sending stuff there, I don't need to know the packet gets lost. Like I can visually see that the packet gets lost. So we use a different protocol called UDP, and the user datagram protocol, which is like a slimmer, less reliable, but faster sort of thing. And all of these things are now working under IP.
Right. Yeah. So everything has an IP address, which is just a address for your computer, so it knows where the data should go. But they split TCP/IP, so it's officially called TCP/IP.
Okay.
That's what it's called now.
So we turned the internet on January 1st, 1983, basically, and it's been running ever since.
No big deal.
We turned the internet on.
This guy's Wayne Gretzky.
Yeah.
This guy's Wayne Gretzky, for sure.
Yeah. Yeah.
Most shots on goal, most goals scored.
Yes. Amazing.
Yeah, that's pretty sick.
So the internet's on, baby. It's going. A lot of people have access to it. Suddenly you've got this distributed network that can send packets between computers, super long distances. You can share information. You can remote log into super powerful computers. This internet thing is pretty rad. And before we break into the next act, I just want to tell this really funny story. First, you got to know that Vint Cerf wears a three-piece suit to literally everything.
I looked him up on Google Images.
Yeah.
You are correct.
Yes. Like he is like this white beard, white hair, three-piece suit. Like he is a serious
awesome.
man. He's so dope. Yeah, he looks really good in it. And I've been calling him Internet Zaddy for quite a while now because that's what anyway. Yeah.
Title of the podcast.
Internet Zaddy. I have that written down for some reason. Anyway, he has this funny story where he's at an Internet Engineering Task Force meeting, which is like these meetings that they were having to talk about internet protocols and stuff in 1992. And he does this strip tease in his three-piece suit. And under the suit, he has a shirt that says IP on everything. Because at the time, he was trying to push the adoption of internet protocol being on all networking equipment. And like nobody was really having it. So he does a freaking strip tease at this internet meeting.
I'm glad the inventor of the internet was an OG memer.
Yeah.
Yes.
It was like off the net memeing right here. Anyway, it works and it becomes the foundation of the internet and home networking and the Internet of Things. And basically all the technology that we use right now that does networking is based on TCP/IP. And this guy made it in like 6 months. Incredible.
Well played.
Yeah. So there's more to that story. Quite a bit more to the story, and it gets very interesting. So we're going to explore that after the break. All right, we're back. So the internet's on, and it's working, and it's scaling really, really fast. Originally it scaled very quickly. Originally on the ARPANET, there was no central address book for these computers. You know, each network node had its own address book that was sort of maintained by the network administrator, but there was no way to prevent duplicates in the address book or update the address book network wide. So when all these networks came together to form the internet, that was a problem, and it was scaling really quickly. You know, this is the Act 2 is called the DNS, and it's very abridged because we did an entire episode on the DNS.
I was gonna say this sounds like it could lead straight into last episode.
It basically could. Yeah. What you could do is you could like listen to last episode and then come back if you really wanted to. But think about this: when TCP/IP was introduced, it introduced the idea that every computer needed an address. So if you think about packet switching again, you realize it's important that each packet of data knows where it's going. So of course it's bouncing off all these network nodes, trying to find the path of least resistance to get there as fast as possible, but it needs to be sent to a specific address. So back then, if you were a computer at UCLA and you wanted to get on a computer at UC Berkeley, you had to type in the IP address to connect to that computer. This was mostly fine at the beginning when there was only a certain number of computers on the network. But there was only 4 universities there were only 4 universities connected at the very beginning. So you had this very small list of IP addresses. But the internet scaled very quickly. There were already 400 connected when the internet got turned on. And can you imagine having a spreadsheet of like 400 computers, each with different IP addresses, and every single time you wanted to connect to one, you had to like look through the spreadsheet with your granny glasses and find, which IP address was correct? Like, not great.
Were IP addresses always in the format that they are today? Which is like
there have been different. There's like IPv4, IPv6, and that basically just like adds extra digits, which exponentially scales the amount of computers.
That's what I'm thinking. Like at the time, there's only 400 computers, so if we just have like a 4-digit IP address, we're good.
Yeah.
And then suddenly that's not.
Well,
enough.
there are many stories of people being like, "Oh yeah, IPv4, like that'll last for the next 500 years." No, it did not. Not even close. Now I believe we're on IPv6 right now, and that should last a while, but who knows? We're making a lot of devices because every individual device that connects to the internet needs a unique IP address. Yeah, it's crazy. We talked about this in the ICANN and the 7 Keys of the Internet episode, but the original solution to this IP address indexing problem was one guy named John Postel. He created a document called host.txt that would contain every single computer's IP address.
From that,
So, you'd call up John, you'd be like, I want to connect my computer to the internet. And he'd be like, okay, so you're this IP address, and I'm going to put you. And then he would distribute this host.txt spreadsheet to the entire internet, and you download the host.txt spreadsheet
yellow
every
pages
day.
of the entire internet.
Yeah, basically. Because he was handling the assigning of IP address, he became known as the IANA, or the Internet Assigned Numbers Authority. Very similarly, there's a lot of redundant information, but I'm just trying to skim over it. Go watch our ICANN and the 7 Keys of the Internet episode. Yeah. So this was not a scalable solution. So a call of proposals on how to improve that system was made. And a man named Paul Makapetris came up with the DNS, or the Domain Name System, which was a way to automatically map domain names or word versions of IP addresses to the server's actual IP address. Became a lot easier. It's very lightweight. It's very elegant. It's great. So while all this DNS stuff was happening, Vid decided maybe he should go and join the private sector. Right? He'd been working on government stuff for like a very long time, and he was interested in trying something new because, he just created the internet, basically. He's like, you could go do something in the private sector and make a lot more money.
Side hustle.
I was gonna say, is he still getting paid like garbage at this point?
Pretty much.
Nice.
Yeah, no, he was he literally told us like, I want to send my daughter to college. So I think he was he was like, I could make a lot more money in the private sector. His 2 sons to college, sorry. So right before ARPA turns the internet on, like right before they turn the internet on, but he had it ready, everything was ready. He left and went to go work for this company called MCI.
It starts with the office equipment you've already got. It ends with a message delivered to anyone, anywhere. Faster, cheaper, or both. It's MCI Mail. And it's what business uses to communicate, when communicating means business.
This is very much business.
Windows Movie Maker.
Yeah.
1983.
I was gonna say that's
came
the
out.
80s encapsulated.
Oh yeah. So effectively, MCI Mail was basically an early version of commercial email, because before this, digital messaging like email was only available to government employees and the university researchers. There was no like public version of email at that time.
Yeah.
Yeah. So nobody had a lot of access to this stuff. So MCI started putting computers in places like hotels, business centers, airports, or you could get them at home if you were rich enough to have an actual computer. You could boot up your MCI like software, right? So it was basically email for rich people or business people.
And it wasn't connected to this new internet.
Yeah.
Like MCI was leasing their own telephone lines from the phone companies and building their own. That's why it was like it had to be a separate thing, because like David said, like you had to be doing government research if you wanted internet access at this point.
The internet was still only for government people and military.
And this is the private side.
And this is the private sector.
Okay.
Yeah, because the technology was there. So some MCI has spun up and they were like, we could do this on our own network, right? So MCI mail was actually really cool because it did some other really wacky things. Like you could enter a physical address into the address bar and it would send a letter.
Oh, I was gonna make that joke.
No, literally.
That's a joke. But okay. Yeah.
Literally, yeah. You would pay different rates based on like what kind of communications platform you wanted to use.
That's hilarious.
So if you thought like, oh, I want to send this MCI mail to this other person, but I'm not sure they're going to get it in time, send it in letter format to this guy's hotel. It was like business, big business.
A pigeon would take off with it.
Yeah. So Vint actually launched MCI Mail. He went to MCI to build MCI Mail for MCI, and he launched it very quickly in September of 1983, which was the same year they turned the internet on, right? Like he left ARPA right before they turned the internet on, built this email client for MCI, and they launched it that same year, which was pretty wild. And I think it went kind of okay, like the launch of MCI Mail. This was like the first commercial email service. I think they were expecting it to be like insanely profitable because Mint saw like the value of the internet and being able to communicate like that. But it didn't really turn out that way. They tried a lot of different marketing campaigns to try to get people to use MCI Mail, but it just didn't gain a ton of hype. It took a while. They were just too early, basically. And that'll happen, So Vint stayed at MCI for a while, like 8 years, but he got pretty bored again because, he created the internet. He's probably wanting to do something.
You're just itching for that next.
Yeah,
that
and you're
next high.
Exactly. Yeah, and so Bob Kahn, who was actually the guy who went to Vint to try to get him to build TCP/IP for the military, had just created this new nonprofit called CNRI, or the Corporation for National Research Initiatives. Basically, a think tank. If you know what a think tank is, just like we do all this research and then we sell it to the government or something like that. So Vint went to do that instead because it was just way more fun. Like they got to like just build a lot of random different stuff. So they gallivant together on this 8-year exploration of what the internet could be used for, because it just got turned on. They were the only ones that knew how valuable it was. And so, they started making all this crazy stuff like digital libraries, mobile software, knowledge robots, which were basically early forms of AI. Jesus. Yeah, for 8 years, they were just like, let's go freaking wild, and just made all this crazy stuff. But in the background, this is over the course of 8 years, there's a lot of stuff developing in the internet community. Like the National Science Foundation decided that they wanted to connect 3,000 universities to the internet. And remember when the internet got turned on, it was only 400 computers. Yeah, computers, not even just universities, like 400 computers.
Oh, wow.
Oh.
Yeah. And they want to connect 3,000 universities. So what they were going to do was build a multi-network system, or something called an internet backbone. So basically, like, there are clusters of computers, of servers that run the internet, right? Right now we have like Google and Facebook. And like, these are all these servers that are just giant clusters that route your data around. That's called an internet backbone. And then all of a sudden, the Department of Energy and NASA decided that they also wanted to create these big clusters, these internet backbones. And by the mid-'80s, there were suddenly 4 different massive government internet backbones that were growing. And that required a lot of networking equipment. So during this period, there was suddenly a huge influx of networking equipment manufacturers that were popping up to create the backbones, right? Because suddenly you're like, oh yeah, we need 3,000 universities connected, but we have no equipment
To fill that need.
Yeah.
Yeah.
So people are going to come in and make money.
Mm-hmm.
But something happened around this time that made Vint realize that he needed to get the internet into the hands of the public. and that the internet was going to be a very big deal. Because again, still only for research universities, but is growing so quickly. But Vint has this story where in 1988, he went to an internet trade show, which just became a thing at the time, which was basically just networking equipment manufacturers that were showing off their stuff. Yeah. But he saw all these companies that had these huge booths and huge displays and huge TVs that were like, and he's like, oh my God, like people are putting real money into networking equipment. Like this is like millions of dollars of stuff. Yeah, it made sense. I mean, over this time, it became pretty clear that personal computing was blowing up. The Apple Macintosh came out in 1984. Personal computers were getting really popular. They had their own personal software that ran locally. So people were getting computers in their homes. And Vince like, oh, these are computers and we have the internet. I mean, they were made to go together, right?
Hey, you got your computer and my internet. No, you got your internet and my computer.
But the governments and the universities were the only ones that had access to the internet, which, you know, for the people who knew how useful the internet was really freaking useful. So Vince at this trade show and he's seeing how much money is being thrown at it. And he realizes that if the general public could get access, that the internet could be a self-sustaining entity. Because again, like these millions of dollars are being put into the industry that are only being sold to the government, military, and universities right now. But what if the public suddenly became a customer? You know, you have this really limited amount of people and it's still blowing up. Then all of a sudden it's just like everybody. The biggest industry of all time is about to explode.
Yeah, and I mean, and government funding always is like, it's a question mark. Like this, in the start of this, all happened because the government basically stopped funding ARPA, DARPA, whatever it was back then.
Exactly.
They got to the point they were so small that they had to work on this project.
Yeah.
And I'm sure they've got that in the back of their minds, like, we could lose this again.
Yeah.
Yeah.
It could be like a huge waste of money, right? But the problem was one big thing needed to change before this was going to be put into the hands of the public. That was the law. Because even with stuff like MCI mail, there's only one application that people had access to. If you wanted to be on the actual internet and you wanted to grow, something needed to be done to get people on that thing. And Vint went full gangster mode. He's like, how can I break the law?
Nice.
Yeah.
And so I remember thinking in 1988, how are we going to get the general public access to the internet? And I thought, well, there's a problem because there was something called an appropriate use policy of the government backbone networks. You could only use them for government-sponsored research. That was the basic rule. And so I had to figure out, how could I break that rule?
How do I break this rule that only allows the government access to the internet? So he has this idea. What if he's able to put MCI mail, which he just made for a private company, the commercial email service, not just on MCI's network, but on the internet, like the internet. He's like, well, first of all, this wasn't even necessarily made to be on the internet. Like, I don't really know. The protocols were made for a local network, not necessarily the internet. And I don't even know if this is going to work, but I also just want to break the rules because I want to see if I can get commercial traffic on the internet, right? So in 88, he goes to the Federal Networking Council and he asked them, can I hook up MCI mail to the internet? And they said yes.
Nice. There are no rules.
Yeah.
It's easy to break the rules when they just let you do it right off the bat.
Exactly. It was like he was very like, I'm not even sure if they knew what they were agreeing to. They
Probably
probably
not.
didn't because he's an internet person and they're just like, oh, technology. I don't know. You do your thing, right? But they did. And so now, all of a sudden, anyone that was using an MCI mail was also interacting with people on the internet. So suddenly you had commercial traffic flowing over a government service hosted by public universities. None of these things are ever supposed to touch. These are three separate organizations that are not supposed to be intertwined.
Can't be commercialized unless we get the government to change its policy. So as a relatively new employee of CNRI, a couple of years into working there, I went to the Federal Networking Council and asked them for permission to hook up MCI mail, commercial email package, to the internet. My purpose was twofold. I wanted to see what would happen if we did that because the two systems were not necessarily designed to work. And second, I wanted to break the policy logjam that said you couldn't put anything commercial on the internet. I figured until we did that, we'd never be able to turn it into a self-supporting system and it would never spread, at least not much. Well, much to my astonishment, they said yes.
Which is just crazy. Yeah. So naturally, other email providers would started saying like, wait, that's not fair. Because at this point in time, MCI mail was not the only. Yeah, there were other ones that were popping up.
Yeah.
And everyone's like, why does MCI get to be on the internet and we have to have our own little local network? Like that's a private organization that has like a weird deal with the government. Very strange. So the government becomes in a jam, or as it puts it, in a log jam. I mean, they let this happen. They opened the floodgates, right? So they had to let other businesses connect to the internet too. They couldn't just only let MCI connect to the internet. So you can imagine the surprise when people suddenly they're not in these little silos of services anymore. Like imagine that you're using WhatsApp and you get a WhatsApp message in Telegram or iMessage all of a sudden. You've got these separate apps and you're used to using WhatsApp, and all of a sudden someone who messages you through Telegram just comes into your WhatsApp. You're like, that's really weird. That's basically what was happening. Like all these independent protocols just opened up. And pretty rapidly, infrastructure started to pop up to route people to the internet. These became internet service providers, right? Because all of a sudden the public has access to the internet through these commercial services, and these things like MCI mail or their competitors became the internet service providers that we know today.
So you needed the person to be the at-home private citizen, having their stuff connected into this now network of government and private citizens,
right,
and universities and everything, because they didn't know, they couldn't get to there before.
Yeah.
So someone had to lead them to water. Yeah.
Right, lead them to water.
Yeah.
MCI was connected now to the internet, but they had to connect you into the internet because you had just been connected to MCI before. So this is the funny thing. People are technically, like on the internet now, but in a very limited way. Like they're just trading data. They're not browsing the web. And notice that I used web for the first time. Things don't actually start heating up for another 10 years. There's just all this periods of time between all of this stuff. And now we get to the creation of the World Wide Web.
So what year are we in now?
1999.
Hey, Ellis and Adam here from the Waveform Podcast. Despite the fact that we've been researching this story for almost a year, both of us somehow missed David saying that the World Wide Web was invented in 1999. The World Wide Web was actually invented by Tim Berners-Lee in 1989. So, if you will, for the next 3 or so minutes, just imagine David saying 1989 every time you hear 1999. Thanks.
So now we get to the creation of the World Wide Web. A man named Tim Berners-Lee at CERN came up with an idea. You may have heard of this man. So the internet's already running. It's already connecting the world with very basic applications. But isn't the point of the internet to share information and not just share like data and applications?
Yeah.
Yeah. Were you going to say something?
I agree.
Okay. Yeah, so that's happening, of course, but like primarily in the sense that you were going to be using individual web pages. You're going to specific web addresses and websites, and you're consuming the information that was available on those websites. That was all that was happening at the time. So, like, how do you research now? Like, what's the best way to jump around to different